Good afternoon, students. So in the last class we discussed the things, and then now we are going to the effects of the torque on the rigid body. Last class we had discussed. So now we are going to start the next topic, that is work done by the torque. So what is that work done by the torque? Is nothing but, let us consider a rigid body rotating about a fixed axis. So shows a point P, and then see here the diagram will elaborately given whatever the things has to be done. So let us consider a rigid body rotating about a fixed axis that shows a point of P, that is denoted here, and then by rotating about an axis perpendicular to the plane of the page. So a tangential force is applied on the body, that the force is F. So if the force is applied to the body, it produces a small displacement, that is ds, on the body. So the work done dw by the force we are going to calculate. That is dw. We know that work done is nothing but force into distance, and here what is the thing has to be means only for the small displacement we are going to calculate the small work done. That's why we are taking this as dw, that is equal to f into ds. So as the distance ds, the angle of rotation d theta and the radius r are related by the expression, that is nothing but ds is equal to r d theta. So the expression for work done now becomes dw is equal to fds and dw is equal to fr d theta. That means ds we are know the value, so that's we are substituting here. Now the term fr is a torque, that is the tau produced by the force on the body. So tau is nothing but the force into the r, so the distance or the radius of it. So we are taking that as a torque produced by the force on the body, that is dw is equal to tau into d theta. This expression gives the work done by the external torque tau, which acts on the body rotating about a fixed axis through an angle of d theta. So the corresponding expression for the work done in translational motion is dw is equal to f ds. Understood what is? So if you are applying a force to the thing that is on the body, means it will displaces, but the displacement has to be very small one, that is ds. So what is the work done for that ds we are going to calculate, that is dw. So for that only we are calculated all these things. So dw is equal to f ds, that is the work done by the torque. And next we pass on to the next topic, that is kinetic energy in rotation. Let us consider a rigid body rotating with the angular velocity of omega about an axis. So every particle of the body will have the same angular velocity omega and the different tangential velocities v based on its position from the axis of rotation. Okay, two velocities are here. One is an angular velocity omega and the tangential velocity is v. Let us choose a particle of the mass m1 situated at the distance of mi, situated at the distance of ri from the axis of rotation. It has a tangential velocity, so vi we are taken, that is given by the relation of v is equal to r omega. We already know that. That's why vi is equal to ri omega. So the kinetic energy of the particle is nothing but kei is equal to of mi vi square. So writing the expression with the angular velocity, so instead of writing v, we are going to write that as r omega. So that is equal to half into mi ri omega whole square. So if you are whole square it, you will get that half into mi ri square omega square. So for the kinetic energy of the whole body, which is made up of large such particles, the equation is written with the summation. So the kinetic energy is we are considering for the full body means, so it will be having more particles. No, that's why we are taking as a summation. Summation means n number of particles will be there. That's why we are taken as a summation. So therefore kinetic energy is equal to of into summation of mi ri square omega square, and that will becomes where the term summation of mi ri square is the moment of the inertia I of the whole body. So moment of inertia I, that is summation of mi ri square. We already know that also, because already we see that moment of inertia. So therefore, I is equal to summation of mi ri square. So the expression for the kinetic energy of the rigid body in rotational motion is Ke is equal to of I omega square. Of I omega square. How you are getting this of I omega square? Instead of writing that summation of mi ri square, we are writing that as I. That's why we are getting this equation. Kinetic energy is equal to of I omega square. So this is an analogous to the expression for the kinetic energy in translational motion. So that is become K is equal to of mv square. Okay, so that is the thing. So relation between the rotational kinetic energy and angular momentum is nothing but the rigid body of moment of inertia I rotate with the angular velocity of omega. So the angular momentum of a rigid body is L is equal to I omega. So rotational kinetic energy is nothing but of I omega square. So multiplying the numerators and the denominator of the above expression with the I, we get the relations as L is equal L and Ke as Ke is equal to of I square omega square by I. We are multiplying I by the denominator and also the numerator. So it will become of I omega whole square by I. So I omega is nothing but L, no. So it becomes Ke is equal to L square 2I. So this is the expression for the kinetic energy in rotation. Understood? Next we are going to see the power delivered by the torque. Power is delivered the work done per unit time. If we differentiate the expression for work done with respect to the time, we get the instantaneous power. That is P is equal to dW by dt. That is equal to tau d theta by dt. dW is equal to tau d theta, that is P is equal to tau omega. The analogous expression for the instantaneous power delivered in the translational motion is P is equal to F dot V. So this is the analogous expression for the instantaneous power. Next we are going to see the comparison of the translational and the rotational quantities. Many quantities in the rotational motion have the expression similar to that of the translation motion. The rotational terms are compared with the translation equivalents. That is given the tabulation form. Translational motion is a displacement x, but here rotational it will have the angular displacement theta. Here both the motions will have the time t only. Velocity here in the translational v is equal to dx by dt. But in rotational omega is equal to d theta by dt. Acceleration in translational dv by dt. In the rotational alpha is equal to d omega by dt. So in translational mass is m, but in rotational it is moment of inertia I. So in translation F is equal to ma, in rotational torque tau is equal to I alpha. Here linear momentum P is equal to mv, here it is angular momentum L is equal to I omega. Impulse F del t is equal to del p, in translational angular pulses tau d del t is equal to del L. Work done W is equal to Fs in translational, that is W is equal to tau d theta in rotational. In kinetic energy, rotational is equal to of I omega square, but in translational of mv square. So for the power P, P is equal to Fv in translational, but the power P is equal to tau d omega. Next we are going to see the topic as a kinetic energy in a pure rolling. In general, pure rolling is a combination of the translational and rotational motion. We can write the total kinetic energy as the sum of the kinetic energy due to translational motion and kinetic energy due to the rotational motion. That is Ke is equal to Ke trans plus Ke rotate. If the mass of the rolling object is m, the velocity of the center of mass is Vcm we are taken. So moment of inertia about the center of mass is ICM. Then the angular velocity is omega. Then Ke is equal to of mv square. So m we are using as a capital M, and v, that is vcm square, plus icm omega square we are using. So that is two things, that is one for the rotational, so we are getting mv square, and for the for the translational we are having mv square, and for the rotational we are using ICM omega square. So with the center of mass as a reference means the moment of inertia of a rolling object about the center of mass is ICM is equal to mk square and VCM is equal to r omega. Here k is the radius of gyration. So k is equal to of m VCM square plus of mk square VCM v square cm, that is r square by r square. K is equal to of mv square VCM square plus of mvcm square k square by r square we taken as common, and these two will be equal, no? So we are taken that as an equal. The common factors has to be taken out, that is k is equal to of mvcm square. If we are taken out, that means 1 plus k square r square we are getting. So next we are going to see the with the point of contact as a reference. So we can also arrive the same expression by taking the momentary rotation happening with respect to the point of contact. That is another approach to rolling. So if we take the point of contact as a O, then k is equal to of I naught, that is I o omega square. So that is moment of inertia of the body about the point of contact. So when the parallel axis theorem, I naught is equal to ICM plus mr square. So therefore we can write that I naught is equal to mk square plus mr square. So with VCM is equal to r omega, or omega is equal to VCM by r. So we have substituted that in the equation. So we are getting k is equal to of m k square plus m r square VCM square by r square. So here also we are taking that of m VCM square as a common. So then we are getting the equation as 1 plus k square by r square. So as the two equations are same, it is once again confirmed that pure rolling problems could be solved by considering the motions as any one of the following two cases. The combination of the translational motion and the rotational motion about the center of the mass, and the momentary rotational motion about the point of contact. So these are the conditions. These two are very important. You will get this in the 3 mark or 2 mark. So pure rolling problems could be solved by considering the motion as any one of the following two conditions. What are the conditions means? Combination of the translation motion and rotational motions about the center of mass, and the momentary rotational motion about the point of contact. These two are very important conditions. Next we are going to see the last one, that is nothing but rolling on inclined plane. Let us assume a round object of the mass m and the radius capital R is rolling down on an inclined plane without slipping. So there are two forces acting on the object along the inclined plane. One is a component of the gravitational force mg sin theta, and the other is a static frictional force F. So the other component of the gravitational, we know that mg cos theta is cancelled by the normal force exerted by the plane. So as a motion is happening along the incline, we shall write the equation of our motion from the free body diagram. So that is given here. So we already seen this type of diagrams, normal and mg sin theta, mg and then mg cos theta, everything. So this is a rolling on inclined plane. So for translational motion, mg sin theta is a supporting force and F is a opposing force. So mg sin theta minus F is equal to ma. For rotational motion, let us take the torque with respect to the center of the object. Then mg sin theta cannot cause a torque as it passes, but the frictional force F can set the torque of Rf. So Rf is equal to I alpha. Using the relation A is equal to R alpha, the moment of inertia I is equal to mk square. So we get that Rf is equal to mk square A by R, and then we are getting that force is equal to ma into k square by r square. So now we are writing the equation mg sin theta minus ma k square by r square is equal to ma. So mg sin theta is equal to ma plus ma into r k square by r square. So we are taking that cancelling the, if we are taking that ma as a common means m and m will get cancelled on both the sides, and we are taking a as a common, so it will becomes 1 plus k square by r square, that is equal to g sin theta. So we are rewriting this acceleration. We are getting a is equal to g sin theta and the other will come on the denominator side. So we can also find the expression for the final velocity of the rolling object by using the third equation of motion by the inclined plane. That is v square is equal to u square plus 2as. If the body starts rolling from the rest, u is equal to 0. When I is the vertical height of the incline, then the length of the incline s is equal to h by sin theta. So v square is equal to, we are going to substitute that. V square is equal to 2 into g sin theta 1 plus k square by r square into h by sin theta. That is equal to 2gh. Sin theta get cancelled. So 2gh by 1 plus k square by r square. So taking the square root of this, you will get the v value, that is v is equal to root of 2gh by 1 plus k square by r square. The time taken for rolling down the incline could be written as from the first equation of the motion, that is v is equal to u plus at. So for the object which starts rolling from the rest, u is equal to 0. So what is t? T is equal to v by a. So t is equal to, we are substituting the v value and also the a value, we already found out it. So from that we are solving this 2 and we are getting what is the final equation, that is t is equal to root of, what you will get, 2h 1 plus k square by r square by g sin square theta. That is the final value of it. Okay, and the next, the equation suggests that for a given incline, the object will least value of the radius of gyration k will reach the bottom of the incline first. Okay, so this is for your 5th unit, and up to this you are having for your portion for the second term.